Good morning, ladies and gentlemen. My wife is worried about the title of my paper, that it's too long, and you may all fall asleep before you finish reading it. The title actually means that everything in this presentation is aimed at producing durable concrete structures, where durability is most needed, and that always means the cover zone. My main focus will be not on the concrete structures, but on the structures of formwork and reinforcement into which the concrete is poured. I want to take you inside these cages to help you appreciate the problems faced by the concrete workers. These problems are mainly about access. Access for concrete, access for vibrators, and access for workmen, so they can do all the things listed here without too much discomfort. Finally, there has to be access for light, so that the flow of the concrete can be observed, even at the bottom of the pour, and particularly as it forces its way through the outer Rio bars and into the cover zone. Problems occur when concrete doesn't flow. It has to flow from the pump down to the bottom of the pour, then along the bottom, around all obstructions, through the gaps in the Rio bars and into the cover zone. The challenge is to get concrete into a cage like this so that it drops cleanly to the bottom and then spreads outward and upward, filling all intended voids, and particularly the cover zone between the outside reinforcement and the forms. The white wavy lines indicate how the surface level of the cover concrete rises progressively as it is forced out through the available gaps in the almost solid wall of reinforcing bars. Problems arise when this doesn't happen, as in this big foundation plinth. So what happened here? It looks like a cold joint where the bottom layer lost its capacity to flow before the next batch of concrete was placed on top. But this disaster could have been prevented. And how do we know that the good concrete is really as good as it is supposed to be? Now here's another problem. The problem's in Pier X, not in Pier Y. It was the designer's fault in the first place. See how the throat bars in Pier Y stop short enough to provide some sort of access? However, in Pier X, the throat bars extended full length and blocked off all access, even for pump hoses or chutes. It's difficult to control a vibrator when operating only from the top of a tapered column like this one. The designer's detailing for the throat bars was a major cause of the failure. Nevertheless, it was still gross carelessness on the part of the contractor. He's supposed to prevent such problems, even when they are caused by the designer. One way to overcome such a problem, without requiring a design change, is to use self-compacting concrete, as shown in this video clip from the Swedish Road Authority.
In the final year of this millennium, SNRA Construction and Maintenance is counting on completing about 10 bridges using this new self-compacting technology. What then has been the motivation behind the change in technology? It all began in Japan in the mid-1980s, where, because of the poor durability and inferior construction quality, a way was being sought to reduce the influence of the so-called human factor, which often led to variations in the quality of the concrete. It was found that the major variations in quality as far as durability was concerned depended on the vibration.
Self-compacting concrete may be the answer to a number of difficult concreting problems. But self-compacting concrete requires a very high level of control at the batching plant, and many plants aren't able to achieve this level of control. Vibrators are likely to be necessary for quite a while to come, but it is absolutely imperative that the flow of the concrete be observed intelligently. This may not be easy to do, as the next slide illustrates, but if it isn't done, we may get major areas of non-compaction, like the examples we have just seen. So just sit back for about a minute and watch the concrete flow and listen to the song of the vibrators. Down through, inside, down to the bottom, lovely. 3 slides deal with the problems of concrete production and supply. I've tried to make them a bit provocative. These problems have been around for a long time, like how do you measure the free water in the aggregates? Or how do we know that we have got the water-cement ratio we specified? We still don't know the answers to such questions. The reason that we have shut our eyes to these problems for so long is because our thirst for concrete has been strength-driven. Superplasticizers have enabled us to use very low water-cement ratios, so it is not hard to keep even the wettest mixes below the specified maximum. But now we are finding our bridge decks are cracking all over the world. This slide tries to give an overview of the challenge facing the mix designer in producing durable concrete. 0.35 is a typical target value for the water-cement ratio of a mix which is required to meet common durability criteria for concrete in a marine environment. If you're planning to use self-compacting concrete, then you will have to keep all batches within the limits of say 0.33 to 0.37 or even tighter. But for conventional concrete, you must assume the batches will vary between 0.31 and 0.39 for the same nominal mix. In terms of potential durability, these are orders of magnitude apart. How can we hope to make reliable service life predictions if we can't control our concrete any better than this? Having looked at the concrete supply problem, I'll just throw this slide up to remind you again that concreting problems such as these need to be recognised and solved at the design stage before the detailed drawings are finalised. It is not good enough to build major problems into the reinforcement detailing and then expect the contractor to find a solution at the last moment. There must be a much closer connection between the construction specification and the design specification. Construction planning has to be built into the design process. What is more, these construction planning requirements have to be built into the contract between the owner and the designer. The designer must be contractually committed to building constructability into the design and its detailing, and the owner must enforce this commitment. When I throw this slide up, many of you will shudder, because your experience of quality assurance on construction contracts has been very negative, if not disastrous. However, ISO 9001 is not the problem. The principles of ISO 9001 are brilliantly simple and effective, at least in the 1994 version. They are all about identifying potential problems and developing preventive procedures to avoid or minimise those problems. However, for each contract there must be a separate QA specification which links relevant clauses of ISO 9001 to each of the construction clauses where they need to be applied. For example, to comply with the ISO 9001 requirements for process control, the contractor must identify those conditions which could adversely affect each process and prepare documented procedures for controlling those conditions so that the quality of the product won't be adversely affected. This slide gives an example of a concreting process in which there are several major problems to be solved. Some of these are listed here. It is up to the designer to identify these problems first and to ensure the QA specification is effectively worded. The contractor must demonstrate in his detailed construction procedures how each of these potential problems will be overcome. In order to prevent concreting failures, there are two more very important phrases in ISO 9001 which construction engineers and design engineers need to understand and to provide for at all stages of planning and execution. These phrases are special processes and continuous monitoring. ISO 9001 defines special processes as those processes you can't verify by testing or inspection after the process has been completed. ISO 9001 says that such processes must be continuously monitored. It's fairly obvious that most critical concreting processes are special processes. Therefore, to comply with ISO 9001, we need to provide the right people, experienced inspectors, to watch with their own eyes to see that the concrete really is flowing as it needs to be. and not running out of energy, as happened to the concrete shown here. It was in the hollow flange of this curved box girder that the problem occurred. Actually, it only occurred in one short section, which says a lot for the skills of the concreting crew. But you see, the designer has made a problem by requiring the concrete to be forced through a narrow gap for 2 metres without providing any access. Note the man in the brown shorts. He was our resident QA inspector and the hero of the day. The men on the left of this slide are the contractor's good guys. The man on the right is my senior QA inspector, checking that these guys are fully aware of the problem and are observing the concrete flowing out from underneath the void forms. But then the good guys went off for lunch. The relief crew weren't up to the job, and this is what happened. Our QA inspector was convinced there was a problem, but the contractor didn't want to smash his formwork open to check it out. Even our resident engineer was nervous about forcing the contractor to open up. But my senior inspector and I trusted the competence of our site inspector and persuaded the resident engineer to take the risk. Fortunately, our actions were vindicated and proper repairs were carried out. Now, you can't do this sort of thing unless the QA provisions of the contract are practical and enforceable. In my last 5 slides, I'm taking an opposite view to those who would say we have to eliminate the human factor. My argument is that it is because we have tried to eliminate the human factor that we are falling behind the Romans. These basic concreting skills can be resurrected, and they must be, if we are to leave a mark which lasts into the next century. Eugène Freycinet had part of the answer. If you haven't read the story of his life, I encourage you to do so. He was a very practical visionary, and his mathematics and his concrete research had only one purpose: to make pre-stressing work. But he would have never made it work if he hadn't been able to lead his construction crews by example. He really was a carpenter, a steel fixer, and a concreter, and his men knew it. You might call this slide trying to do things the Freycinet way. After all, he had to learn the basic trade skills the hard way. That's why he knew what men could do and what they couldn't do. When I refer to construction workers as being the bottom, this is not a bad phrase. They provide the foundation. But if those at the top don't get the right messages, then they will make the wrong decisions. We need engineers who have had their boots in concrete to take their place at senior management level. The trouble is that it may take too long before these site-experienced engineers make an impact at the top. What we all want to see is item number 5 on this slide: predictably durable concrete structures, with the emphasis on predictable. That means that we can have confidence we won't see rust marks in 10 years, when the designer hoped for at least 50. We won't get 5 unless we have 1, 2, 3 and 4. But my experience tells me that at the practical level, the prospects for 1, 2, 3 and 4 are getting worse. That's why we need to go right to the top. God is very interested in rocks. After all, he made a lot of them. However, unlike many chief executives, God has time for people and their problems. He fully understands our technical problems at every level, from political to submicroscopic, and he knows all the answers. Perhaps you think I'm foolish, but it seems logical to me that God, who commands us to do good works, also wants us to make good concrete and to make structures that last. Thank you for your attention.